Hi everyone. In the last class we have discussed about self-adjoint and positive operators. Today we will be discussing about normal operators on a Hilbert space. So let us quickly recall. Let T be a bounded linear operator defined on Hilbert space H. Then T is said to be normal if T star T equal to T star. So one important example we have seen was the multiplication operator induced by a continuous function. So let us take phi from CAB. In fact, we can take phi from L infinity AB. Define m phi from L to AB into itself by m phi at f is nothing but phi f for every f in L to AB. So this is a multiplication operator induced by phi. So here phi f is a function acting on t is nothing but phi t multiplied by f of t for every t in AB. We have shown that m phi star is exactly multiplication operator induced by phi bar, where phi bar at t is nothing but phi of t bar for every t in AB. And we can easily show that this is a normal operator. M phi star m phi, we get this m phi bar m phi, this is m mod phi square, and this is nothing but m phi bar, this is again m phi star. Hence we can conclude that the multiplication operator induced by phi is a normal operator. We can slightly generalize this result. So let us take x sigma mu, let us take x sigma mu be a sigma finite measure space and phi you take from L infinity of x sigma mu. So define m phi from L to x sigma mu into L to x sigma mu by m phi at f is phi f for every f in L2 of x sigma mu. Then as in the earlier case, we can show that m phi is bounded and norm of m phi is exactly essential supremum of mod phi. We can show that essential supremum of mod phi, and m phi star we can show to be m phi bar in the same way that we have proved earlier, and we can show that in this case also this is a normal operator, and this operator is very important in operator theory because this is a prototype for all the normal operators, in the sense that given any bounded normal operator on a Hilbert space H, we can show that that is unitarily equivalent to a multiplication operator induced by a function phi coming from L infinity of x sigma mu for some sigma finite measure space X sigma mu. So this is called the spectral theorem for normal operators. This one version called the multiplication version of the spectral theorem. This will be proving at a later stage. So from that point of view, we can say that the multiplication operator induced by a function coming from L infinity space is very important. And a special case of this we have already seen, that if you take, so let us take lambda n in L infinity. So we have defined t from L2 into L2 by t of x1, x2, x3 so on is lambda 1 x1, lambda 2 x2, lambda 3 x3 so on for every xn in L2, and this is nothing but a diagonal operator with diagonal entries lambda 1, lambda 2, lambda 3 so on. So the matrix of T with respect to the standard orthogonal base of L2 is nothing but lambda 1, lambda 2, lambda 3 on the diagonals, and this is with respect to the standard or the normal basis of so clearly this is a normal operator, because if you compute t star at y1, y2, y3 so on, this is lambda 1 bar y1 comma lambda 2 bar y2 comma lambda 3 bar y3 so on for every yn in L2. That means the matrix of T star with respect to the standard orthogonal basis is the infinite diagonal matrix with the diagonal entries as lambda 1 bar, lambda 2 bar, lambda 3 bar so on. So we can easily check that T is normal. So these are two important examples of normal operators. Next, let us see some important characterizations of normal operators. So let me write as a proposition. Let T be a bounded operator defined on H, then the following are equivalent. The first one is T is normal, and the second one is T star is also normal. So the proof is very trivial in this case. T is normal implies T star T is T star. Now we can write this as T star double star T star double star T star. So this implies T star is normal. On the other hand, once T star is normal, then star is normal, that is T is normal. So this is otherwise also trivial. Okay, this is a simple characterization of normal operators. We have one more important characterization of normal operators, namely let T be in B of H, then the following are equivalent. T is normal if and only if norm Tx equal to norm T star x for every x in H. So here also the proof is simple verification only. T is normal implies that T star T equal to T star, and this implies T star T inner product x with x is inner product T star x with x for every x in H. Now apply the adjoint definition to conclude that norm Tx square is nothing but norm T star x square for every x in H. This implies norm of Tx is nothing but norm of T star x for every x in H. On the other hand, suppose, so this is nothing but the proof of 1 implies 2. To show the proof of 2 implies 1, if norm Tx equal to norm T star x, then you can square it, you will get norm Tx square equal to norm T star x. So let us look at 2 implies 1. Norm Tx equal to norm T star x for all x in H implies that norm Tx square equal to norm T star x square for every x in H. This implies that inner product Tx with Tx is nothing but inner product T star x with T star x for every x in H. Again applying the definition of adjoint as in the earlier proof, this is T star Tx inner product with x equal to, this is T double star T star, but T double star is T star inner product x with x. This is true for every x in H. So this implies that T star T minus T star x inner product with x is 0 for every x in H. Okay. Now from this we can conclude that this is true for every x in H. Now we know that this operator is self-adjoint. We can easily show that T star T minus T star, if you take the adjoint you will get the same operator. So it is self-adjoint. Now we know that if you have a self-adjoint operator T and inner product Tx with x is 0 for every x, then T must be 0 operator. So let us quickly recall. If A equal to A star and inner product Ax with x is 0, this implies A is 0, because we know that norm of A is nothing but supremum of, so norm of A is supremum of mod inner product Ax with x for every x in the unit sphere. So that implies this is 0. Once norm A is 0, then we can conclude that A must be 0 operator. So from this we can conclude that this operator T star T equal to T star. This completes the proof of 2 implies 1. So we have proved that T is normal if and only if norm Tx equal to norm T star x. One immediate corollary we can write is the following. Since norm Tx equal to norm T star x for every x, whenever x is coming from null space of T, we get norm Tx is 0. From that we can conclude that norm T star x is also 0. That means x is also in null space of T star. So corollary, if T is normal, then we have null space of T equal to null space of T star. But we know that null space of T star is nothing but range of T perp that we have already seen for any operator. That means when T is a normal operator, null space of T and range of T are orthogonal to each other. Okay, that means whenever T is 1 1, then T star is also 1 1. So this is the second one. T is 1 to 1 if and only if T star is 1 to 1. Okay, so this is an immediate consequence of the earlier characterization theorem. So we have one more important consequence of important characterization of normal operator. So that is given by the following theorem. So to prove the theorem, we need an important result for general bounded operators. So let me quickly recall. So if Z is a complex number, then we can write Z as x plus iy, where x and y are coming from R. So this decomposition is known as the Cartesian decomposition. Of the complex number Z. Okay. Now, if T is a normal operator, we can also write T as A plus IB, where A and B are self-adjoint operators, and A and B also commute. So we can compare the set of all normal operators with set of all complex numbers. Here when we write Z equal to x plus iy, we know that x and y commute with each other. So we prove the similar kind of result for normal operators also. But before going to normal operator, we prove a general theorem. Let T be a bounded operator on H, then there exists a unique pair of operators, in fact self-adjoint operators, A and B, such that T equal to A plus IB. So we have already told that unique pair of operators, that means this representation of T is unique. So this representation is known as the Cartesian representation or decomposition of T. Here we are not saying anything about commutativity of A and B. When T is bounded, we can only say that T can be written as A plus IB, where A and B are self-adjoint operators, and yeah. Okay, so let's try to look at the proof of this one. Now the proof follows from the complex version of Cartesian decomposition. So we know that x is nothing but z plus z bar by 2. So here x is z plus z bar by 2 and y is z minus z bar by 2i. Similarly we can write, so write A as T plus t star by 2 and b as t minus t star by 2i. Then we can easily check that a is self adjoint and b is also self adjoint. And not only that, if you write also, we can say that t equals to a plus ib. This is trivial to verify. Now if there is another pair of self adjoint operators, C and D, such that t equal to C plus id, then we have t star is C minus id, because C and D are self adjoint. Hence we can have, if you look at t plus t star by 2, you will get C is t plus t star by 2, that is A, and D is t minus t star by 2i. If you look at that, you get exactly B. Okay, so this is the Cartesian decomposition of a bounded operator. This is similar to the Cartesian decomposition of a complex number, but when we take complex number z equal to x plus iy, we know that x and y commute. But when we put a condition ab equal to ba here in this result, we can conclude that t is normal. So one important corollary. Let t equal to a plus ib be the Cartesian decomposition of t, then we can say that t is normal if and only if ab equal to ba. Okay, so once we prove this once we prove this result, we can say that normal operators are exactly generalization of complex numbers, because when we have a complex number, we can write z as x plus iy, where x is z plus z bar by 2 and y is z minus z bar by 2. Similarly, we can write for a normal operator in the Cartesian decomposition form as a plus ib, where ab equal to ba. And we know that when z equal to x plus iy, this x is known as the real part of z. This is real part of z, and y is imaginary part of z. And in this case also, a, whatever we are writing a, so this a is known as the real part of a, real part of t, and b is known as imaginary part of t, similar to the complex numbers. Okay, so let us try to look at the proof of this result. So t equal to a plus ib implies t star is a minus ib, because a and b are self adjoint. Now if t is normal, t star t is nothing but t star. This implies a minus ib multiplied by a plus ib must be equal to a plus ib multiplied by a minus ib. This is nothing but, so this is a square plus iab minus iba plus b square. This is nothing but a square minus iab plus iba equal to b square. Now after cancellations we can actually say that these four terms get cancelled. Then we can say that 2iab equal to 2iba. So this implies ab equal to ba. We wanted to prove ab equal to ba. Okay. On the other hand, suppose ab equal to ba, then we can actually conclude that 2iab equal to 2iba. Now from that we can actually expand t star t and t star and conclude that t star t equal to t star, and then it is easy to check. T star commutes with t star, concluding t is normal. Okay, so this is one of the important characterization of normal operators. Let us look at some more important observations about normal operators. If t is normal, then we can conclude that t plus lambda is normal for any lambda in the complex plane. This is easy to check. The second one is if t is normal and p is a polynomial with complex coefficients, then we can say that p of t is also normal. Okay, and one more important property is that let t be a normal operator, then the sister algebra generated by identity operator t and t star is a commutative unital sister algebra. So if we denote this sister algebra by sister of I t t star, this is a sister algebra generated by the identity operator t and t star, then we can this is nothing but the smallest sister algebra containing I, t and t star. This is nothing but, we can easily show that this is span of polynomials in t and t star, where p is a polynomial in two variables z and z bar. Okay, so the algebra generated by I, t and t star consist of all polynomials in I, t and t star, and the sister algebra also contains cut here. Okay, now one can easily check that if t is normal, cut here. If t is normal, then we can easily show that norm of t square is nothing but norm t whole square. Also from this we can show that norm of t power 2n is nothing but norm t 2 power n for any n bigger than or equal to 1. Okay. So these are some information about the class of normal operators, and here we have a problem. Let S and T are two normal operators. S and T be normal. Under what conditions S plus T and ST are normal? This is a natural question. In general, we can show that sum of two normal operators need not be normal and product of two normal operators need not be normal, but under certain conditions we can show that the sum and product of two normal operators is again normal. So we can find the necessary and sufficient conditions. Okay, so this is information about normal operators. In the next class we will be discussing about a special class of normal operators, namely unitary operators, and a more generalized class than unitary operators, namely the set of all partial isometries. So I will stop here. Thank you very much.